Good afternoon, everyone. I am Aritra. Today I am going to present my dissertation on the topic towards quantum mechanics. Let's go through the topic. Before starting the topic, first of all, we need to know what is mechanics. We use the term quantum mechanics, classical mechanics, but mechanics actually deals with the study of motion when subjected to forces and the subsequent effects of the bodies on their environment. Simply, it is the interaction between the force and matter. Matter refers to the macroscopic objects around us. So, when we speak about macroscopic objects, we need classical mechanics. Here is the father of classical mechanics, Sir Isaac Newton. So, it is also known as Newtonian mechanics. In the midst of the 19th century, physicists claimed that they had achieved all success in discovering the laws of nature, and if there exists anything new, they could explain it by the existing theories. Then why do we need quantum mechanics? Actually, the development of quantum mechanics began in the year 1900 with Planck's study of light emitted by heated solids. So we start by discussing the nature of light. In 1803, Thomas Young gave convincing evidence for the wave nature of light by observing diffraction and interference when light went through two adjacent pinholes. In 1864, Maxwell gave four equations, known as Maxwell's equation, which unified the laws of electricity and magnetism. In the late 19th and early 20th century, more precisely to say from 1860 to around 1930, a number of beautiful experiments were observed, but scientists were unable to explain the science behind those phenomena. The first one is Rutherford's alpha particle scattering. In this experiment, he bombarded a very thin gold foil with alpha particles. The experiment concluded that the entire mass and the entire positive charge is concentrated in a very small part of the atom called nucleus. But he failed to explain the stability of the electrons. Also, he failed to explain the hydrogen emission spectra. It is observed that line spectra is obtained instead of continuous spectra. Though Niels Bohr successfully explained the atomic spectra, but he failed to explain the relative intensities and fine structure. Another experiment is called blackbody radiation. What is blackbody radiation? First of all, a blackbody is one which can absorb and emit radiation of all frequencies. This is called blackbody radiation. So based on the classical theory, attempts were made to explain the Lumar-Pinzham curve or LP curve, however it led to ultraviolet catastrophe. Though Rayleigh and Jeans were able to explain in the high lambda region of the curve and Wien in the low lambda region, we got two expressions for one curve. Later on, Planck gave a satisfactory explanation over the entire lambda region. Another experiment, heat capacity of monatomic solid. What is heat capacity? Heat capacity is the amount of heat to raise the temperature by 1 degree centigrade or 1 Kelvin. Dulong and Petit drew a conclusion on the basis of classical law of equipartition that each atom or molecules behave as a harmonic oscillator having energy equals to 3 kT. So we have Cv equals to 3R, but experimentally it is found that this value is observed at high temperature only. And lastly, the photoelectric effect. What is photoelectric effect? It is the emission of electrons when electromagnetic radiation such as light hits a material. The present theory at the time that kinetic energy of electrons should only depends upon the intensity of the light, but it actually depends upon the frequency. So we have seen all these experiments gave some unsatisfactory results to describe the microscopic phenomena. That means classical mechanics fails to describe it. We have observed light and electrons both behave like wave and particles through various experiments. Both wave and particle nature of the radiation are associated with the energy according to the following relation given by Einstein E equals to mc square and by Planck E equals to h nu. So equating both of them we get lambda equals to h by mc or lambda equals to h by p. Here p is the momentum of photon. We cannot measure m and c separately, so we have to measure p here. This equation actually represents the wave-particle duality, where P represents the particle nature and lambda represents the wave nature. Famous scientist de Broglie or de Broglie extended the extended that not only light but also all matters show wave-particle duality. He proposed that superposition is inevitable and electron shows wave as well as quantum nature. He proposed that relation once again, lambda equals to h by p. Here p is m into v. This m and v can be measured separately, and lambda is the Broglie matter wavelength. And finally, Heisenberg stated that it is impossible to determine both the conjugate variables simultaneously with precision. It has been observed for a quantum mechanical particle that a certainty in one introduces uncertainty in another. So till now we have seen how we gradually shift towards quantum mechanics from classical mechanics. But here is a hidden fact. Actually, India is the reservoir of knowledge and wisdom from the very beginning of the civilization. We have seen that in various fields of physics, chemistry, mathematics, everywhere India has a major contribution since the era of Aryabhatta, Barahmihir, and even before. So such comments are not unexpected. So let's have a glance. Long ago in the city of Würzburg, Germany, a young boy was born with a curious mind and an insatiable hunger for knowledge named Werner Heisenberg, and his passion for physics and mathematics would shape the course of life forever. It was not far ago the Nobel Prize was awarded to a brilliant scientist for his groundbreaking discovery, the uncertainty principle. It was the most pivotal and transformative ideas in the entire field of quantum mechanics. Amidst the fervor of nuclear research, Heisenberg's quest for the knowledge went far beyond the boundaries of a lab. With passion for wisdom and a fascination for Indian culture, he sought to unlock the secrets of the universe and learn from the greatest minds of his age. His journey led him to the sacred land of Shantiniketan. He, with the newfound knowledge, he knew that he had to seek out the wisdom of Rabindranath Tagore, one of the greatest philosophers of his time. Together with other leading scientists like Niels Bohr, Louis de Broglie, and Erwin Schrödinger, they formed a formidable alliance driven by the thirst for knowledge. This quote highlights the Vedantic idea that everything in the material world, including matter and energy, is illusory or Maya, and ultimately derived from the Brahman, which is similar to the Heisenberg uncertainty principle. This profound idea planted a seed in Heisenberg's mind and started to see the limitations of classical mechanics. Finally, he realized that a new framework was needed to account for the wave-particle duality of atom. This principle challenged the classical understanding and stated that it is impossible to know both the position and momentum of a particle with absolute certainty. So that's all about. These are some references. This is my acknowledgement. And finally, thank you.